All right, now for a biggie. Now on the tests, on the paper test, notice that there are 7 points for each row. That's a total of 21 points for one problem. Must be important. Well, it is important, and I do want you to be able to understand going back and forth across these, well, what some tricks are in order to figure out how to figure out the answers to this problem. On the D2L test, of course, things are going to be slightly different in terms of computing the BCD and the two's complement and so forth. But let's just hopefully going through these problems will give you a good idea of how to convert back and forth between decimal, unsigned binary, two's complement binary, and biased 127 notation, and unsigned BCD. So first of all, let's just look at some tricks. Notice that unsigned binary and two's complement, these two are very closely related. In fact, all the columns are closely related. But unsigned binary and two's complement, if you're looking at the positive values, and how do we know that it's a positive value? Well, for specifically for two's complement, it has a sign bit, the most significant bit, of 0. So if you've got an 8-bit value that starts with a 0, and then you have the 7 bits that follow it, if this is an unsigned binary or two's complement, they're going to be the same. So if you're looking at something like this problem, the second row, where I have an unsigned binary number that starts with a 0, well, that starting with a 0 indicates that it's going to actually be exactly the same in two's complement binary. So we just simply copy 0, 0, 1, 1, 1, 1, 0, 0. It's that easy. This is true for two's complement and unsigned binary with any number of bits. If the most significant bit is a 0, in other words, unsigned binary is not using it for magnitude, and two's complement binary is not using it for a negative sign, then you just map back and forth. They just copy back and forth. So let's look at these other problems. So 23, let's start out with 23. 23. Well, I can make my little rectangle here with my different powers of 2. And I've got the ones place, the twos place, the 4, 8, 16, 32, 64, 128, right? Now, we look for the largest power of 2 that is less than or equal to 23. We see that there's 16. So I pull a 16 out, and I've got 7 left. That means I don't have 128 in it, I don't have a 64, I don't have a 32. I also don't have an 8, but I do have a 4. So let's pull a 4 out. We're left with 3. I have a 2, so I pull out a 2. I'm left with 1, and I have a 1, and that gets us all the way down to 0. So 23 in unsigned binary is 0, 0, 0, 1, 0, 1, 1, 1. Now notice, it starts with a 0, so guess what? It just copies over. All right, that was pretty easy. Heck, just with that, we've got 6 points just for understanding how to convert to unsigned binary and noting that the most significant bit represents a sign in two's complement and magnitude in unsigned binary. All right, so bias 127. What is 23 equal to in bias 127? Well, remember, what we're looking at in bias 127 is that the patterns of ones and zeros that go in 8 bits from 0 to 255 get shifted, this is unsigned, get shifted for biased 127 so that the patterns get mapped to negative 127 up to positive 128. So somewhere along in here is 23. What does the pattern look like? Well, understand that what we have to do is take our 23, we have to add it to 127 in order to figure out what the corresponding unsigned pattern of ones and zeros would be. So 127 added to 23 is 150, right? And so we take our 8-bit, the powers of 2, so 1, 2, 4, 8, 16, 32, 64, 128. There is a 128 in it, so we put a 1 there. Pull that out, and what we've got left is 22. So there's no 64, there's no 32, but there is a 16. So we pull out a 16, we've got 6 left. There's no 8, but there is a 4. So we pull a 4 out, we've got 2 left. So there is a 2, but there's no 0. So the answer for bias 127 is 10010110. Now another way of doing this, notice that we added 127 to this. Well, we could have done this in binary, so we could have taken the 00010111 that is unsigned binary, or 2's complement. Let's look at the 2's complement. And then we add 127 to it, which is a 0 followed by 7 ones. So 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 0 plus 0 is 1. Notice that that value is exactly the same as the value that we got before. All right. All right. So let's make a little space here. Get rid of some of this garbage. Not garbage. Very important stuff, right? All right. Now, next, we'll leave BCD to the end. All right. So, all right. So, let's go to the next one. Now, what I have is the unsigned binary value 00111100. And what this is once again the powers of 2. So I have the 1's place, the 2's place, the 4, 8, 16, 32, 64, 128. So what is this equal to? Well, it's equal to, there's a 32, there's a 16, there's an 8, and there's a 4. We add these together, we get what? 60? Okay. And in fact, this kind of makes sense because this 4 ones is actually 15. And I've shifted it left by 2 positions, so that's times 2 squared. 15 times 4 is equal to 60. So it looks like, yeah, we got the right answer. So that is 60. Now for bias 127. So we take 127, we add 60 to it to get the offset, right? So we're going to map this to the range of unsigned binary. So this is 187. Now, we do our patterns of ones and zeros diagram, right? So we've got our little 8 slots here with 1's place, 2, 4, 8, 16, 32, 64, and 128. There is a 128 in it, so we put a 1 in that position, and we subtract 128 from this guy, and we get what? So that's 59. All right. There's no 64, but there is a 32, so we pull out a 32, and we get 27. All right. 27, there is a 16, so we pull a 16 out, we get 11. There is an 8, so we pull out 8, we get 3. There's no 4, but there is a 2, and there is a 1. So, biased 127 is going to be 10111011. Now remember, we have a way to double check this. We take the 2's complement value, 00111100, and we add 127 to it, a 0 followed by 7 ones. So we have 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 0 plus 0 is 1. So this guy equals that guy, so apparently we've done it correctly. Now in the third row, we are given bias 127. Now to work backwards from bias 127, remember the reason for the bias was to allow a pattern of ones and zeros that the sequence matched the sequence in unsigned binary going from all zeros to all ones, but we make it so that we shift it down the number line negative 127 by negative 127 so that we can represent negative numbers. So this value right here, first we're going to start out by converting that 0, 0, 0, 1, 1, 0, 1, 1. We're going to convert this guy to unsigned binary, as if it were unsigned binary. So there's the ones place, the twos place, the fours place, 8, 16, 32, 64, 128. So it is 16 plus 8 plus 2 plus 1. We add those guys together, we get 24, 26, 20, what is it, 27? Okay. All right, so 27. What do we do with 27? Well, because we wanted to have negative numbers, we have to shift it down the number line by subtracting 127 from it, and we get negative 100. So the decimal value is negative 100. Okay, now a couple of quick things. First of all, unsigned binary. Unsigned binary only allows us to represent non-negative values, so we have to place an X here. Notice that I ask you to write an X in the columns where you cannot put that value when it's out of the range. Negative 100 is outside the range of the non-negative values represented by unsigned binary, so we put an X there. That's 2 points right there up front. All right, it can't be represented. But 2's complement binary can represent it. Now, how do we do that? Now, remember that you have to have the ability in 2's complement to represent both positive and negative numbers, but we do so by doing that bit flipping thing, that inverting of the bits. We do this by first figuring out what is positive 100. Well, positive 100, let's go ahead and figure out our pattern of ones and zeros for positive 100. So there's the ones place, the twos place, the 4, 8, 16, 32, 64, 128. So 100 has a 64 in it. So we put a 1 in the 64 position, a 0 in the 128 position, and we get 36. That has a 32 in it, so we pull a 32 out. That leaves us with 4. So there's no 16, no 8, but there is a 4. There's no 2 and no 1. So positive 100 is equal to 0, 1, 1, 0, 0, 1, 0, 0. That is not negative 100. To make it negative 100, we have to do the bit flippy thing. So starting on the right-hand side, we copy down all the zeros up to and including the first one. The remaining bits, we invert. And so this is negative 100. And we put it, and notice that the sign bit, that most significant bit, is equal to a 1, indicating it is, in fact, a negative number. So we do, what is that? 1001, 1100. And by the way, we could check to see if we made a full circle. If negative 100 is equal to 1001, 1100, what happens if we add 127 to it to see if we can get back to the biased 127? Well, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry the 1, 1 plus 1 plus 1 is 1, carry the 1, 1 plus 1 plus 1 is 1, carry the 1, 1 plus 0 plus 1 is 0, carry the 1, 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. That 1 gets discarded because it's sign adjustment. That equals that. And we have the correct value. We see that we've made the full circle, and we must not have made a mistake because it worked out to wrap back around to bias 127. All right. Now, unsigned BCD, and whenever I say unsigned BCD, if you remember from our discussion that adding there's a sign, you can have a sign with BCD, and it's usually done with a number that's tacked onto the end, a nibble that's tacked onto the end of the BCD number. In this case, we're just interested in the magnitude itself. We're not worried about the pluses or the minuses. And so it's a pretty easy mapping. If you recall, when we did the hexadecimal to BCD conversion table, what we were looking at was we're going to have a nibble that represents the ones place. And so the unsigned BCD, there's a nibble that represents the ones place and a nibble that represents the tens place. That's as much as we can represent with 8-bit unsigned BCD. If there's a hundreds value, we've gone beyond 8-bit and it can't be represented. So unsigned BCD, for this negative value, we're just going to put an X down here. But what do we have for 23? Well, for 23, in the tens place, we have 2 tens, right? So there's going to be 0, 0, 1, 0. 3, there's going to be 3 ones. So we have 0, 0, 1, 1. And so our unsigned BCD value for 23 is 0, 0, 1, 0, 0, 0, 1, 1. All right. Now, what about for the value 60? Will 60 fit? Well, 60 is less than 100, so in fact, we will have room to fit 60 in 8-bit unsigned BCD. There are 6 tens and 0 ones, so the answer is 0, 1, 1, 0, 0, 0, 0, 0. Wow, that was a marathon session. But if you understand how to fill out this table, you should have no problem converting back and forth between bias 127, 2's complement binary, unsigned binary, and unsigned BCD, and be able to understand how the numbers are represented inside the machine, and possibly be able to debug any problems you would encounter because of things like overflow.